Hi, Algebra 2 Honors students. This is going to be functions day 4, and you can find these notes on page 28 in your packet. So if you want to take that out and get started. Today, the main topic will be talking about inverse functions. And you can see there's two functions given to us at the top, defined as f of x and g of x. And because we already know how to do this with some evaluating, what I'd like you to do is calculate f of 5, g of 11, and then there's two compositions that I want you to calculate. G of f of -1, f of g of 5. See what you get for those results. And then we're going to try and maybe draw some conclusions about what we think is happening with these results. So hit pause because I'm going to go through the answers right now. Okay, if you're done with those three questions, we've got f of 5 is 11 and g of 11 is 5. And then over here, f of -1 would be 2. If I do that inside part first, g of 2 is -1. The composition on the right side, you would do g of 5 first. G of 5 is 1, and f of 1 is back to 5. So notice how in these compositions, the original input is eventually what the output became, right? So g of f of -1, the final answer was -1. F of g of 5, the final answer here is 5. And although this wasn't a composition, maybe you're drawing some conclusions from this as well, that f of 5 is 11. And, oh wait, but g of 11 is kind of back to 5. So what's going on here? I mean, when I input into one that output, if I plug that output into the other function, we get the same input again. So the connection here is if I then asked you to figure out, without a calculator, what's f of g of pi? The answer, I'm pretty confident, is going to be pi. Now, if you do it on the calculator, it's going to tell you 3.14, right? Because it's not going to most likely leave your answer in terms of pi. It will give you that decimal equivalency there. But when we're dealing with these functions in particular, the input for the composition winds up being the final output in the end. And the reason why is that these functions that I gave you for f of x and g of x, they happen to be inverse functions of one another. So that's the main idea. Okay, so f of 5 is equal to 11. Then if g is the inverse function, g of that output would return the input of 5. So here's what I want you to write in the kind of conclusion section below. The two functions above are inverses. They essentially undo each other. What one operation does, when I plug it into the other function, it kind of reverses it and brings us back to where we started. Right? Think of it from that perspective. Inverse functions do have a specific notation that we'll use. So inverses, the notation for the inverse of f of x is f to the -1 of x. So it's like this little -1 exponent up there. Some good information to know if two functions are inverses. If f of x and g of x are inverses, the domain of the function f of x would equal the range of its inverse, g of x. And meanwhile, the range of f of x would be the same thing as the domain of the inverse function, g of x. And that knowledge is actually super important because if I asked you, how are we going to find the equation for an inverse function? If I gave you the function f of x and I say, find the inverse function, g of x, or notationally, you might write it as f to the -1 of x. How might we consider doing that? Well, the domain, which is the x values, become the y values of the inverse, and the y values of the function become the x values of the inverse. So, sounds to me like we better switch x and y. And that's the whole key idea, is that to determine the inverse of a function, we're going to go ahead and switch x and y. So to analyze inverses a little bit further here, I have some examples below of some mappings. The mapping diagrams show two functions and their inverses. We're going to complete the mapping diagram for each. Go ahead and take a look at function A, function B. See if, based on what we just said as far as switching x and y values are concerned, switching that domain and range, go ahead and fill in the missing parts of those mappings, and then we'll make some conclusions about it. Okay, so here's what we got for function A. The inverse function, the domain value of -3 would map onto 0, right? Because originally the domain value of 0 mapped onto -3, so it switches for the inverse. And if you look at function A, The range value of 2 going backwards should map onto 2 elements of the domain. So now if it's the domain value of 2, it's going to map onto 2 elements in the range. And it's a little bit easier maybe to look at function b here, right? If you just simply switch the domain and the range values here, you can see what that correspondence looks like. Now, we talked about this correspondence yesterday in the notes. What's going on with function b, but not necessarily with function a? Well, it's that concept of one-to-one. So which of these functions is one-to-one? It's b, because every input has a unique output, and every output has a unique input. Which function has an inverse that is also a function? Well, if I take a look at this example here, here's the inverse domain value of 2. That doesn't have a unique output. It maps onto 2 outputs in the range. So with this one-to-one correspondence that function b has, b is the one that has an inverse that is also a function. So what are we going to write then in the conclusion section at the bottom of the page? If a function is one-to-one, that's what we determined up here, then that means its inverse is also going to be a function. So when something passes the vertical line test and the horizontal line test from yesterday's notes, what I know about that is that that function's inverse also happens to be a function. So we're trying to connect some of the vocabulary and the main ideas in this unit. Inverses now will definitely have a role in our discussion of what it means for something to be one-to-one. Okay, if we go on to the next page here, we have an example at the top where we're going to find the inverse based on a set of ordered pairs that are given. So those set of ordered pairs, these coordinate points right here, they're graphed already on the set of axes over here. What I want us to do is write the inverse of this function, and then we're going to use the grid to plot where that inverse would lie. So the inverse is going to be found pretty easily for the set of ordered pairs, because remember, all we're doing is switching the x and the y values. So instead of having -4, -2, we're going to have the point -2, -4. And you know what, while I'm at it, why don't I actually just go ahead and plot that so I don't forget about it later on. 0, -3 is going to correspond with -3, 0 for the inverse. So that's right there. Then we're going to have 2, 1, 2, 1. And then finally, 1, 4 would be the last point that determines the inverse of this function up here. So 1, 4 is right there. So the next question is, well, now that I have the function, the original dots that were plotted, original points, and its inverse graphed on the same set of axes, what is the graphical relationship between a function and its inverse? Well, there's sort of a big hint here. I probably could have made this a little bit more exciting per se, or exciting as this is going to get here, by not including this line, maybe. But since this line is here, I hope that you can see that there's really this nice correspondence over that line y equals x. And in fact, it winds up being a reflection over the line y equals x, which is something from geometry last year, right? We definitely reflected over the line y equals x when you learned about transformations. So if you wanted to even get fancy on me, you could use a lowercase r. That's a standard notation for reflections. And then as a little subscript, put y equals x to indicate that that's the line that we're reflecting over. Okay, so that's an important concept too, and that makes sense to me because if you remember the rule from last year with reflecting over y equals x, what happens? The coordinates switch. You switch the x and the y values. And switching x and y now in our context with functions means that we're talking about an inverse. So what we're going to do is get a little bit more practice finding inverses. It's not always going to be that we just have coordinate pairs to switch the order. If we have an actual function, an equation that we're working with and we want to find its inverse, here are 4 steps that we'll use to find the inverse algebraically. Step 1, replace f of x with y. So that's kind of just a quick step, but to make step 2 easier, it's nice instead of saying f of x equals for the function, just to have y equals to start. Because then we're going to switch x and y. That's what we said earlier is happening for inverse functions, right? That x and y get switched when we find inverses. Once you've switched to x and y, then you're going to solve for y again. The main reason why that's a necessary step is so that we can then graph the inverse. Otherwise, simply just switching x and y, you've already established an equation that represents the inverse. of what you started with initially. But we can't easily graph that until we get y equals. And finally, replace y with maybe the appropriate notation. F to the -1 of x looks nice. That step, maybe not as important in the grand scheme of things. If you forgot that, I'd probably leave it. But most commonly, you will see this notation used when talking about inverses. So let's do this next example right here. So it says find the inverse of f of x equals 3x plus 4. Graph the function f of x and its inverse on the same set of axes. So let's go ahead and take a look at, first of all, finding the inverse algebraically. So I'm going to take the step 1, which just said replace f of x with y and get started. So y equals 3x plus 4. From there, we're going to switch x and y, so we get x equals 3y plus 4. First two steps take no time at all. Step 3 is most time intensive in certain examples, as now we have to isolate y, solve for y. So I'm going to do that by subtracting 4 to the other side, and then dividing the 3 over to get y equals x minus 4, all divided by 3. I'm going to do two things when I write my final answer. I am going to do step 4, where I replace y with f to the -1 of x. The other thing I'm going to do, just for the simplicity of then graphing this, is I'm going to separate this and divide each of these by 3. So the 1 in front of this x would make this a 1/3 x minus 4/3. Make sure you divide each quantity on top by 3. It's not a requirement that you write it in that way. It's easier for me to graph this, in my opinion at least. You could have left the equation though as x minus 4 over 3 if you prefer to do that. So why do I think it's easier to leave it in this form? It's because this is the equation of a linear function, mx plus b, right? So we know the slope of the line is 1/3. We know the y-intercept is -4/3. Let's go back to the original line, 3x plus 4, and sketch that. So this one has a y-intercept up at 4. And with my slope of 3 over 1, I would have to rise 3 and run 1, which very quickly takes me off the grid here. So I'm going to go down 3 into the left one, which is okay. It's the same slope pattern, right? Same slope count. So go ahead and connect those points right there. That's a pretty straight line that I drew there. Impressive. Okay, now here's what I can do. I can then go over here and say, oh, let me start at a y-intercept of -4/3. That's a little less than -1, and rise 1 and run 3. And there's no issue with that. It's really just a sketch at the end of the day. But how could I be even more accurate? I don't necessarily have to graph this linear function. I could just take some of the coordinates here and switch them, right? Instead of having 0, 4, we're going to have 4, 0. And actually, even once I just have one of those points, switch the coordinates around, instead of rising 1 and running 3, I could go down 1 and to the left 3, down to the left 3. Hopefully it makes sense that if you have a point on the line y equals x, it's not going to change for the inverse when you do that reflection step. So if you connect these points, not bad as well with that line, here's what I have for my inverse graph. And now that they're sketched on the same set of axes, they certainly look like that reflection over the line y equals x. It's probably nice from your end to label these, okay? In terms of graphing, I'm not as picky about labeling axes or quadrants or anything like that. You've probably had teachers in the past that will make you label much more than I will. But if you're graphing two things on the same set of axes, I've done a good job, I think, using different colors here. But I think in the very least, we should be labeling which one's the original function and then which represents the inverse. Now that we've done that example, I have confidence that you can try this before I see you in class again. So go ahead and find the inverse of f of x equals 2x minus 2, and then graph both on the same set of axes. So that brings us up to example 3 at the top of the page. So for example 3, we're going to go ahead and solve for x, it says. Okay. So in solving for x, how am I going to accomplish that? Well, to get x alone, you're going to subtract 3 to the other side. And then from there, you're going to multiply both sides by 2. I don't really like the idea of dividing a half over, because then you have a fraction in the bottom of a fraction on this side. So I would say instead, why don't we multiply both sides by 2 over 1, the reciprocal, to get x alone. So we get x equals 2 times y minus 3. If you want to distribute that across, we get x equals 2y minus 6. And the reason why I had us just solve for x in this case is getting x in terms of y is another way of thinking about inverses. Okay, so expressing one variable in terms of the other. We have that the inverse of the function in example 3 is x equals 2y minus 6. And I'll show you where that comes up in inverse applications in a minute. But what would I actually use to graph this? To graph the inverse, we would actually now at this point switch x and y, because I remember I never actually did that. I just isolated x up here. But to graph, if you switch x and y at this point, you get y equals 2x minus 6. And this graph would represent the inverse of this initial linear function up here. So I know that we're not as comfortable with that. We really like looking at this better probably when it's in y equals form. But why is it important? Because if you're dealing with an application, you don't want to switch and solve. So if we look at the next two questions in inverse applications, the first question right here is dealing with a bowling handicap. So it says, in bowling, a handicap is a change in score to adjust for different players' abilities. This happens in other things like golf. A certain bowling league uses the equation below to determine a bowler's handicap H in terms of their average A. My mom and aunt are both avid bowlers. I don't know if they have a handicap. I'll have to ask them, but they bowl in a league every Wednesday. They just love it. So here's the equation. So the handicap is based on right now the player's average. But what we can do is we can actually solve for A in terms of H, and that's going to represent the inverse of this original equation. So how am I going to solve this for A? Well, the first thing you might consider doing is, without even distributing that 0.9 through, why don't I divide it over? So we get H divided by 0.9 equals 200 minus A. And then from there, continuing to isolate A, maybe in the next step, you'll subtract 200 over. So H over 0.9 minus 200 equals, just be careful because you still have negative A on this side. So from there, you would divide out the negative 1. What that's going to do is it's going to negate the fraction and make the 200 positive. So I'm going to get a little fancy on you here and say that the final answer is A equals, since the 200 becomes positive, I'm going to list that first and put the negative fraction part second. 200 minus H over 0.9. So what's the benefit to having this inverse equation from the original? Well, now if I know a player's handicap, we can determine what their average is based off of this. Okay, so there might be instances where we know the average and we're looking for the handicap, but if it's the reverse and a player knows their handicap, we can calculate their average pretty easily using this new equation right here. And that's what we're going to do for part B. Using your equation from part A, determine the player's average if their handicap is 27. So all we're simply going to do is plug 27 in for H. So their average is 200 minus 27 over 0.9. And this you can just type into your calculator here. You don't want to have to do the work in your head. So 200 minus, I'm going to make a fancy fraction. That was alpha y equals. That's how I just got there. And the handicap was 27 over 0.9. And it seems like their average would be a 170, which, no offense to my mom and aunt, but I know it must be higher than their averages. So I think they're decent, but I don't know if they're quite at a 170. Okay. So the last example in the notes is about stretching a spring, I believe, and I want you to try it. It's the same idea. I give you the equation for L in terms of W. I want you to find the inverse, which means solve for W in terms of L, and then kind of answer that follow-up question. We'll go over this next time I see you in class. And if you have any other questions about inverses, let me know.